Recording is rolling. It is Thursday, May 1st. We're going to start the final exam review. So you guys have this study guide page. I gave you guys a couple days ago. So this has 100 questions on it, and 50 of these questions are going to show up on the final exam. And we're also going to go over all these on Kahoot. It's going to take us a few days, though. So okay. I'm going to try something a little different this year. We're going to, because tomorrow's a short day, so I don't want to get like 2/3 through Kahoot and we run out of time and some other reasons. This might be pretty good. Is the last topic we're doing is quantum mechanics. So let's toggle back and forth. We'll alternate. So we'll do like day of review, day of quantum. We'll just go back and forth. Speaking of the quantum, you guys already have a head start on that. You guys remember yesterday I gave you guys this quarter page of quantum topics and had you guys start putting this journal together. You guys remember that? Okay. So this journal will take a few days, maybe almost a week to put together, but we'll spread that out over a few days. Okay. And we'll start on that tomorrow. Okay. So everybody good so far? And so the format of the final exam, it's going to be open notes. So keep that easy. So no internet access, but any notes that you guys are keeping, any notes that you guys write on the study guide, any pages to give you guys. And the format's going to be the same as what you guys did on the midterm, which is 2 halves. The first half's going to be 50 conceptual questions, 1 point each. Again, we'll come straight off the study guide. We'll go over all the answers. Okay. And then the second half is going to be 10 equation-based questions that are 5 points apiece. Now, I will give you the equations, so then it'll just be up to you to be able to interpret those equations and solve them. You guys think you can do that? And that'll be it. That'll be it. All right, so let's get going on. Oh, and then we'll have about 10 spare minutes today, actually. So I'll play you guys part of a Mark Rober video in class where he's looking at self-driving cars. All right, so here we go. Object thrown into the air will, with the spin, rotates about its. Yeah, center of gravity. Or you say center of mass would be a good choice, but center of gravity, center of mass. Okay. You guys remember when you came back from the break in January, we kicked off with rotational dynamics. So this is a rotational dynamics question. These questions go kind of in order what we've been doing throughout the year. Okay. So rotational dynamics. Okay, you guys got center of mass, center of gravity? Rotate about. All right. I got points on the board. Picture hangs on a wall with a wire passed over a supporting nail. The picture is in stable equilibrium because it's this picture right here. Why is it in stable equilibrium? Yeah, all those go hand in hand. The center mass, center of gravity is directly beneath the supporting nail. If you gave it any push, suppose you pushed it to the right or to the left a little bit, wouldn't actually rotate and its center of gravity would raise a little bit. Okay. And then if you release that force and let it go, wouldn't it just fall back to its original position? Yeah, so those all go hand in hand and they all indicate stable equilibrium. If something's stable, give it a little push, release it, it goes back. All right. You got Jonathan, Alexander, Smiley Moose, Siriana, Peyton, Torque. Okay. Force times lever arm. So isn't that R cross F? R is the lever arm, F is the force. And cross product means you want to have some kind of perpendicular component between those two. Okay. You guys saw a picture of a wrench turning a nut. How about every time you open a door? Guys, why is the door handle opposite of the hinges? Because that would maximize the lever arm, so you can get a greater torque turning on. Okay. So I picked the red one. Guys, what is the red one? What is mass times acceleration? That's not a torque, that's a what? Force. Yeah, is that Newton's second law of motion? F equals ma. Okay. What about the blue one? Guys, what is mass times velocity? Is that a momentum? Okay, remember that? All right. So torque equals R cross F. That's Smiley Moose, Zariana, Jonathan, Alexander, Peyton. You try loosening a nut with a wrench. The nut doesn't give at all. What should you do? Only above. You push with a harder force, right? That could give you more torque. Extend the lever arm. Ooh, guys, if you have 3 times the lever arm, would that also be 3 times the torque? Right? 3 times the turning moment there. Okay. And also make sure that you're pushing perpendicular to the lever arm. That's what the cross product idea is about. Okay, solid. Okay. Guys, isn't true like if you pull parallel to the door, that would never turn a door. Okay. You have to, some kind of perpendicular component. All the above. I got Jonathan, Luciana, Ziriana, Alexander, Peyton. The resistance an object has to changes in its rotational state of motion. There's 2 meter sticks right there. It's called rotational. Inertia, rotational inertia. I got a couple of meter sticks right here. You guys remember these from a few months back? If I close my eyes to pick them up, they feel like the same weight. Is that right? They're the same weight. Okay. But if I rotate them, is which one's easier to rotate? The one that has the masses close into my hand, and one's further out. Yeah. See, the one close to my hand, there's hardly any rotational inertia. But the one where they're spread further out, it has a lot more inertia. It's hard to get going. It's hard to turn around. It's hard to stop. Right? That's more inertia. Right? So, guys, rotational inertia, the formula for that goes mr squared. So it's the mass times its position from the pivot point squared. Ooh, further out, more inertia. Ian, Luciana, Ziriana, Alexander, Peyton. Gymnast moves from extended to a tuck position. Yeah, you would be decreasing your rotational inertia. Did I just say rotational inertia was something about mr squared? Right now, if you were composed of say like a trillion different points, then the aggregate effect of mr squared for every single point is that it gets closer to that axis of rotation. Okay? Now, actually, there's 3 things that happen during this scenario, and I think it's a question coming up pretty soon. So angular momentum is conserved. So it's conservation of angular momentum. Now, angular momentum is I times omega. That's rotational inertia times angular velocity. So your rotational inertia would decrease. That's the answer to this particular question. Okay. And that would force your angular velocity to do what? To increase, right? So decreasing I times an increasing omega would conserve capital L, which is angular momentum. Okay, so all those things are going on at the same time. Object will maintain its angular momentum unless it's acted on by an unbalanced, let's say, external force or torque. Is that true? Yeah, true. This is called conservation of angular momentum. As long as you have a closed system, angular momentum is conserved. So that feeds into the ice skater question. Okay? And the only thing that can change an angular momentum is an external torque, which would be that would involve a force. So then there too. Luciana, Ian, Ziriana, Alexander, Peyton. Ice skater pulls his hands to turn faster. Aha, all above. Right. So the guiding principle is this blue one, that angular momentum is conserved. Right. So that's your starting point. But what is angular momentum? That's I times omega. So here's your I in red, and here's your omega in gold. Right. So your rotational inertia would decrease, therefore your rotational speed would increase. So all that happens at the same time, all the above. Is everybody okay so far? Everybody's doing all right? All right. So we got Ian, Luciana, Ziriana, Alexander, Peyton. Huge rotating cloud of particles in space gravitates together. As the cloud shrinks, it rotates. faster. Yeah. Right. Is that the same as the ice skater question? Same principle, right? So angular momentum conserved, rotational inertia is decreasing because their particles get closer together. Right? So the angular speed has to increase, rotates faster. Just like the ice skater. Jonathan, Luciana, Zariana, Peyton, Alexander. Two people sit on a balanced seesaw. When one person leans towards the center, that person's end will. Yeah, rise. Right. So one way to think of it is here, I should draw this one out on paper. Let me do that. Okay. So let's get a seesaw going. Here, I'll do it before and after. So let's do it before after here. Okay, so seesaw. Right, let's get a pivot point about the center right there. Right, let's get a couple of friends. Say this friend and this friend. Okay. And it starts off pretty well balanced. Okay. Now, one way to analyze this is to look at this pivot point and let's sum the torque about this pivot point that is marked with an X. Okay. So wouldn't that be this radial arm crossed with this force produces some counterclockwise torque, and this radial arm crossed with this force produces a clockwise torque, and maybe the sum of the torque is zero. So I can say the net torque, the sum of the torque is 0 Newton meters. All right, so that is a starting point. Okay. Okay. Now, what if one of these guys leans in? And to make it really obvious, I'll have him just go ahead and scooch way in, like way over here. Okay. Is that an exaggerated effect of the same principle? Okay. So whatever. Well, this guy on the right provides the same torque as he did before, same clockwise torque. That didn't change. Same torque as before. Right? But look, isn't there a smaller radial arm? Now he's got the same weight, right? But the fact that it's a smaller radial arm, isn't that a much smaller torque than before? Okay. So now this whole thing is gonna rotate clockwise as a result. So this whole thing goes this way. And the person that leaned in, I have him walking in here, guess his end, goes straight up. That's the answer to that question. Okay, you guys remember that? All right. So you guys good? Everybody's good. All right. Jonathan, Luciana, Alexander, Ziriana, Peyton. When used horizontally in construction, an I-beam is nearly as strong as a solid bar because what's your I-beam? Yeah, so before the tension and compression are predominantly in the top and bottom flanges. Okay, predominantly top and bottom. Okay. Here, I'll also draw that one out. You guys are write this down. So have an I-beam about like this. So some beam going on. About like that. Okay. Then what if this has a couple of supports at the bottom down here, and I put a big old vertical load right in the middle at the top? Okay. Doesn't this whole thing want to bend? I'm switching color. Guys, does this want to bend like this, like a smiley face? This wants to bend like this, like a smiley face. Okay. And what kind of stresses would we have? Because would the bottom be in tension or compression? Guess it'd be like in tension. Okay, so I'll do this for tension. I'll call it. Well, I'll just spell it out. Tension. Okay, but the top being kind of compressed together. Okay, so that's like this. This goes into compression. For compression. Okay. Now, do you think there's some axis near the center that it switches from tension to compression, and maybe there's very little stress? Right. Right. Which means you don't need as much material in the middle, but you want most of your material in those flanges in the top and bottom parts. Yeah, that's where most of the stress is, most of the tension and compression. Okay. Okay, you guys good? Engineering. Okay, Jonathan, Luciana, Alexander, Ziriana, Peyton. Less force is required to poke through an eggshell from which side? Yeah, inside out rather than outside in. So, okay. Part of this answer has to do with that the material of the eggshell has a good amount of compressive strength, but not very much tensile strength. Right? Wouldn't this also make sense from a biology evolutionary point of view, like why does nature produce that shape? Well, because the little chick on the inside has to get out, but maybe a predator from the outside, you wouldn't want it to get in so much. Okay. Okay. So here goes. Okay. And so maybe here's your chick on the inside trying to get out, but some predator from the outside. More difficult to get in. Okay. You guys ever seen an arch bridge? Could this be an arch bridge right here? Okay. Do you guys think maybe all these stones, right, have a huge compressive strength? So if you're walking across the top, right, you're putting a huge force from the top, right? Doesn't have a huge compressive strength, and so that then your weight is transferred down to the arch like this, right? Right. But what if this was upside down? Right, like if you turn this upside down and this material doesn't have nearly as much tensile strength, it's going to crack apart really easily. It's just going to break apart. Right. Okay, so it's easy for the chick to get out, but it's hard for a predator to get in. Which geometric shape has the least surface area for a given volume? Ooh, okay. I want to see if you guys would know that because there's a Paul Hewitt video that has this, and I realized I didn't actually roll this in class yet, so I'm going to roll it here pretty soon. But here's a different way to frame the same question. What if you have a blob of Play-Doh and you want to put it into a shape so that it minimizes the surface area? What should you roll it into? How about a sphere? Right, it's the same question, right? Or here's kind of the opposite perspective. What if you had some volume, or sorry, wait, how does this go? What if you had some defined surface area and you wanted to maximize the volume inside given some surface area? Like I got some paint, I'm going to paint some surface of something, right? And that's fixed, but I want to maximize the volume. Would that also be a sphere? Right? Same thing? Okay. Here, let's play a couple of Paul Hewitts right here. Oops. Not that. Here we go.
Hi, gang. We're going to talk today about the difference between surface area and volume. This has a certain surface area, huh? It also has a certain volume, amount of space taken up. I'm going to pour this liquid into here, and I'm going to ask you, will it fill up to halfway, less than half, or more? Take a guess. Turns out any object has the least amount of surface when it's the shape of a sphere, a ball. And we find out appreciably more than halfway. Now, why? It's because in this shape here, it had only a little bit of surface area, but the same volume here is here.
Yeah.
You got a drink, you want to cool it. Someone says, put an ice cube. Someone else says, no, crush the ice cube up, then put it in. It'll make the drink cold faster if you crush it up. Someone else said, it's the same amount of ice either way. Makes no difference. You say.
What do you say? Actually, well, that is an executed question. Here, let's roll the executed question, then we'll go back and watch the rest of that. Let's see what you guys say. You're going to find out. We got Jonathan, Luciana, Alexander, Peyton, Ziriana. Which will cool a glass of water faster? Ice cubes are the same massive crushed ice. Ah, 50-50 split. Hey, now, why is the answer crushed ice? What do you guys say? Why? Because what does the crushed ice have more of? Ah, surface area.
Person next to you said, speculate, try it. What's the answer again? How many people say it's the same amount? It's going to cool it the same way either way. Make no difference. Hey, wait a minute though. Hey, wait a minute. No, if you crush the ice, you're going to get a whole lot of little pieces. And a whole lot of little pieces will have more combined area than the big piece. Crush it up.
Yeah, so the transfer of thermal energy happens at a faster rate because more surface area. Okay. The second half of the video goes through a bunch of examples because, like, what if you have a solid baked potato versus if you slice it a bunch of little French fries? Right? Little French fries cook faster. Right? So things like that. What you guys think about lunch here? Olivia, Luciana, Alexander, Peyton, Siriana. If an elephant grows to twice its height, what happens to the surface area of its ears? Changes by a factor of All right, so somebody got it. All right, factor of 4. Now, guys, where does that come from? Did I say the elephant was twice as tall? Here, find a. You got a picture for you guys over here. Now you get this ready. Boom, boom, about this. Okay, give you guys a picture to think about. Right, you guys see a little baby elephant and a big elephant here that's twice as tall. Right, because when you scale up twice as tall, different physical properties change at different rates or change by different factors. Right, so anything linear would also be a factor too. Do you guys think this elephant on the right is twice as long as this elephant on the left, and also twice as wide? If I could see twice as wide, all right, sorry. All right, anything linear. Right? But anything related to area, like asked about the area of its ears, but what about its shadow? Would that also be an area question? Right. So here's a question with the same answer. How big is this big shadow compared to the small shadow? 4 times. You guys, 4 is a linear factor of 2 to the power of what? 2. Isn't it 2 to the power of 2 4 times? Right? Okay. So it'd be twice as tall. Anything linear is twice as much. Right? But anything related to area is that linear factor 2 to the power of 2 because an area is a 2-dimensional concept. Right? But you know what else? I bet there's some 3D concepts. Right? How much volume do you think is the big elephant compared to the little elephant? How much volume? Close. His volumes of how many dimensions are we talking about? 3 dimensions? Well, it's 2 to the power of 3. Aha, aha. Right? Is that true? Right? Okay, guys know. Okay. Which by the way, might have something to do with this big old ears because if you're 8 times the volume, do you think you have a lot more thermal energy that's more difficult to radiate away because right, it's like deeper inside your big elephant body? Right. So, do you think that might be a good reason to have ears that are 4 times as big? Ooh, 4 times as big, right? Even though it's proportional, right? Proportionally scaled up. Got Olivia, Luciana, Peyton, Ziriana, Alexander. An elephant that grows to twice its normal height will increase its weight by a factor of. Yeah, there's guys, isn't weight proportional to mass and doesn't mass occupy volume? So that's a 3D concept. So you take a linear scaling factor of 2, you put it to the power of 3 for 3 dimensions. 2 times 2 times 2. That's where the 8's coming from. Okay. You guys, on your final exam a few weeks from now, what if you have an elephant that's 3 times as tall? Guys, a 3 times as tall elephant would have an area how many times? What's 3 squared? 9. And would have a volume of how many times? 27, because 3 times 3 times 3. Okay. So take the linear factor, whatever that is, right? And then put it to some power that corresponds to the question. Yeah. Olivia, Luciana, Peyton, Ziriana, Alexander. Where is the pressure greater? 1 meter beneath the surface of Lake Michigan or beneath the surface of a swimming pond? Yeah, it's the same. Okay. So do you guys see the formula for pressure was rho GH? Rho is the density of the fluid, which is usually water. G is the gravity field of the planet. And H is how deep you are. Right? And if all 3 are the same, then it's the same pressure. It doesn't matter how big the volume of water is. Right? Same pressure. It's for the same depth. Olivia, Luciana, Peyton, Alexander, Ziriana. Archimedes' principle says that an object is buoyed up by a force equal to. Yeah, oh, wait, well, there you go. Definitely write that one down. The weight of the fluid displaced. Right, so that breaks down to the formula rho GV, where rho is the density of the surrounding fluid and usually water, G is the gravity field of the planet, and V is the displaced volume So if you jump into a swimming pool, if you completely submerge yourself, if you go beneath the surface, that would also be your own volume. But if you're floating on the top, remember, it's only the volume that you're displacing, right? And if we're talking about a force, actually only one of these is even a force, and isn't weight a force, but none of these other ones are even a good option from that unit's point of view. Yeah, right. So, oh, here's another way to think about this. While you guys write that down, right? If you're floating in water and you like froze time and stepped out and you say, okay, there's like a me-shaped hole in the water. You fill that with water and you measure the weight of that water, right? That would be equal to the buoyant force that's holding you up to begin with. Okay? So the weight of fluid displaced. The reason objects in a fluid experience an upward buoyant force. Guys, why does the buoyant force help you float? Why does it push upward? Because there's greater pressure on the bottom? Is that true? Yeah, that's true. That's true. Right. So objects are three-dimensional. So if something submerged in water is floating in water, right? Then there's a depth difference, and there's always more pressure the deeper you go. Right? Even if it's kind of thin like a piece of paper, it's still true. Still a buoyant force upward. Got Jonathan, Luciana, Peyton, Alexander, Ziriana. You squeeze a balloon to half its original size, the pressure increases by a factor of 2. Ooh, one winner. All right, here, bring that over and solve that right over here. All right, so you guys know this is called ideal gas law. Pressure times volume equals number of moles of gas times the constant times the absolute temperature. Is that true? Ideal gas law? Okay. Oh, here, I'll draw a little balloon right here. Okay. Okay. So if you squeeze this balloon to half its original size, well, that would change this V. I'll throw some numbers in. Let's just make up some numbers. Could I say, 6 times 4 equals 1 times 1 times 24? Maybe, yeah, just throw some numbers in. Okay. Now, if you squeeze this balloon to half its original size, let's keep everything over here the same. So it's the same moles of gas inside the balloon. The R is the same, whatever that is, with the units, right? And let's say the temperature also stays the same, which is probably a reasonable assumption, right? If that's true, then guys, what's the only number that fits in this space right here? Huh? 2 times what is 24? 12, right? Is that true? Right. And now, okay, if you didn't see it before, I bet you definitely see it now. You guys see with half the volume, you have to get double the pressure. Is that right? So it's called ideal gas law. Ideal gas law. Okay. But if you're just focused on the relationship between pressure and volume for a constant temperature, like I did here, that's also called Boyle's law. So see both of those. All right. So you guys can navigate the balloon. Okay. If you're mature, make up some numbers, try it out. All right. A balloon is buoyed up with a force equal to yeah, that's the best answer, is the weight of air that the balloon displaces. Like that would always be true. Right? Is that called Archimedes' principle? Because the surrounding air is the surrounding fluid. Right? So rho GV is the formula that goes with that. It's for Archimedes' principle. Right? Now, okay, so somebody did choose the blue one, which actually isn't completely terrible for one specific situation. Because what if you have a hot air balloon, it's just kind of hovering in equilibrium? Wouldn't it be true that the weight down is balanced by the buoyant force up? Okay. And in that case, could the blue answer be true for that specific scenario? Okay. But the general better answer is the green one. All right. Jonathan, Luciana, Peyton, Alexander, Ziriana. 2-ton dirigible hovering in the air. Ooh, equilibrium. The buoyant force acting on it is just kind of hovering there. It would also be 2 tons. Right, so this dirigible weighs 2 tons. There's 2 tons pulling down on it. Right? But if it's in equilibrium, there has to be also a 2-ton buoyant force pushing up so that the net force is zero. Right? So force down, force up. All right. You're standing on the moon and you release a balloon filled with helium gas. What does the balloon do? Yeah, it's gonna fall because if you release the helium balloon on Earth, I'm thinking there would be two forces on the balloon. Would that balloon have a little bit of weight pulling it down on Earth? Yeah, but there's a much bigger force, the buoyant force pushing it up. So you let the balloon go, it rockets straight up into the atmosphere. Right. But does the moon have an atmosphere? No. So can there be a buoyant force on the moon? No. So there's still a little bit of weight, but that's the only force. So it's just gonna free fall straight down. Right? Guys, how about this question? Let's go back to last semester. Suppose you release that helium balloon on the moon, and you release a hammer at the same time. Which one hits the surface of the moon first? Same time, same time. Yeah, because they both free fall. Right. Different forces, different masses, but the same ratio. The gravity field. Jonathan, Luciana, Alexander, Peyton, Ziriana. When a river narrows, the water in the river flows. Yeah, faster. Right? In terms of the speed, it's faster. Right? So this comes from a principle called conservation of flow. So the flow rate, like the gallons per minute, the volume per time, that's constant. Right? But the speed, well, it has to speed up. Right? If it's going from a big pipe to a little pipe, or from a wide river to a narrow river, speed up. Conservation of flow. You blow across the top of a piece of paper. That paper will. Yeah, there you go. Okay, you guys remember that. You can try this too. They were trying this last class. Right? You hold a paper, kind of horizontal, but it's kind of limp. You blow a stream of air across the top. Now, a moving fluid will have a decreased internal pressure. You guys remember Bernoulli's principle? Looks a lot like conservation of energy, but it's in terms of pressure. Okay. So a moving fluid has a decreased internal pressure. Okay, so that would, in that case, vacuum the paper up. There you go. Temperature is mostly related to yeah, looking for average molecular kinetic energy. Okay. So this, do you guys remember that they ran a PowerPoint on thermodynamics? It was one of the first slides where you say, well, what is temperature? Where does that come from? How do you quantify it? Okay. And there's this kinetic energy theory of temperature. So if you get down to the molecular scale, you can watch atoms vibrate. And the more they vibrate, that's going to correspond to a higher temperature back at the macro level. Okay? Guys, the air that we're in right now, is that about, I'm looking at the temperature over there, it says 74 degrees Fahrenheit. Okay. Now, if you could somehow pick out, let's say you picked out like 4 or 5 different particular air molecules, like, oh, there's a nitrogen there, and there's another nitrogen, there's an oxygen, and you're watching them. Right? Do you think they might move individually at different speeds? Yeah, right. But the aggregate effect is that they produce a temperature you perceive as 74 degrees Fahrenheit. So, yeah, average molecular kinetic energy. The reason an ocean's temperature does not vary much from season to season. Yeah, high specific heat capacity of water. Okay? So the temperature of water is very stable. It's hard to change the temperature of water. You guys know that because if you put some water in a pot on the stove and you turn the stove on, doesn't the metal part of the pot heat up really quickly? but that water takes a few minutes to bring up to the temperature you want, right? Also, once that water is hot, it'll stay warm for a long, long time. Either way, it's really hard to change the temperature of water. Back in the PowerPoint, actually, one of these slides coming up, you guys are going to see a table of specific heat capacities for different materials. And compared to other materials, water has a really high specific heat capacity. Since the ocean is made, let's say water, there you go. The temperature of the ocean is relatively stable compared to if it was made out of anything else. Hey, Jonathan, Luciana, Alexander, Peyton, Siriana. Largest extremes in temperature. Guess where does the temperature swing from really hot in the day to really cold at night? Yeah, middle of the continent. Middle of the continent. Okay. Do you see that the other three options that were not the correct answer are all surrounded by large bodies of water? Right? Coastal cities, large bodies of water. Islands, large bodies of water. Near the ocean, oh, large bodies of water. Right? Middle of the continent, I think just a bunch of land all around. It looks like the odd man out there. Okay. So, and I know the ocean has relatively stable temperature. Guys, we're in Florida. Do we have pretty mild summers, and also our winters are also pretty mild? Right, we only get like 2 cold days every year. But guys, who's ever been out to the Midwest? Who's been to the Midwest? Just a couple of guys. Right. So I know a few years back I was driving across South Dakota. It was evening, sun was dropping. It was like 90 something degrees Fahrenheit, so it was pretty hot. Right. And I saw in front of me, there's some kind of storm clouds rolling in. Not a big deal, right? So just keep driving. This storm rolled in off the plains, and it was like a little mini hurricane hit. Yeah, except the temperature plummeted. There was so much rain. Barely see what I was doing. I was driving like 20 miles an hour on the interstate. It's crazy. Had to get off. Right? Yeah, so crazy weather, crazy fluctuations in the middle of a continent, but relatively stable anywhere you're near the ocean. When an iron ring is heated uniformly, the hole in the center becomes what? Yeah, larger. Yeah. So, most materials, you heat them, they expand. So the material itself is going to expand the metal. Right. But that also would be true for the entire object at large and the hole in the center. It all gets bigger, all larger. During a very cold winter, water pipes sometimes burst. Why? Yeah, water expands when freezing. Right. Which is actually pretty weird because most substances, if they go from a liquid to solid, do you guys think most substances occupy less volume going from liquid to solid? Right? But not water. Right? Because if you put an ice cube in water, does that ice cube sink to the bottom of the glass or does it float to the top? Floats to the top, right? Because ice has less density than liquid water. Right? No, why? Why is water an exception to most materials? Do you guys know snowflakes, 6 sides, right? So that crystal pattern. So when water goes from liquid to a solid form, it takes this crystal pattern, like with 6 sides, and that actually occupies more volume, so you get less density. Yeah, water expands when freezing. Heat transfer by conduction. So I'm looking for electrons bump into other atoms and electrons. You guys know conduction is direct contact of surfaces. So, or I should say transfer of thermal energy by direct contact. So surface to surface. Okay? If you get down to the molecular scale, isn't just like electron clouds against the other electron clouds? Okay, so you need direct contact. That's electrons, atoms bumping into each other. Transfer of energy, that method. Okay, so you guys know conduction? Convection is bulk movement of fluids And the best answer there is large numbers of atoms move from place to place. Okay. And so if you have a pot of water on the stove, do you think the water in the bottom is warmer than the water on the top? Right. And that gives impetus for the water to start moving around. That's a convection current. Right. Guys, how about the Gulf Stream going by Florida right now? Is that a convection current? Yeah, convection. You guys got convection? You got Jonathan, Luciana, Alexander, Peyton, Siriana. Heat travels from the sun to Earth. Yeah, electromagnetic radiation. Because isn't the Earth surrounded by the vacuum of space? So that's the only candidate there. Yeah. You guys ready for the last one? Today? Yeah, for the win! For the win! Yeah, Jonathan, Luciana, Alexander, Peyton, Zariana. Who will come out on top? Planet Earth loses heat primarily by well, wouldn't it also have to be electromagnetic radiation? Right? Same thing. Because Earth is surrounded by the vacuum of space, so it's not conduction, it's not convection. Okay? So I'm thinking that Earth has, I'm going to call it three main sources of thermal energy. Right? There's the sun. Right? The sun's radiating energy across space to Earth. Right? So that's one source of energy. Right? There's geothermal. So if you dig way down, like a couple miles, you get a lot of geothermal. Right? Actually, if we could tap into that, that would probably give us like plenty of energy. It's probably good at that, but it's kind of hard to dig holes that deep, right? So that energy is radiating towards the surface from deep in the earth, right? Now, if you just had that as your system, right? We got radiation from the sun, we got geothermal, and then excess energy radiates off into space. That's the answer to that question right there. Shouldn't the Earth be pretty well in balance in terms of temperature? Pretty well in balance, right? If you also include like burning fossil fuels, which we've been doing for about 100 years, right, that's energy that's been stored for about 300 million years. Right? That's when fossil fuels come from, right? That's adding additional energy. Hence, we have global warming from that additional burning of fossil fuels, right? Storing excess energy from the sun too. Right, so they go. How that? Right? With the bronze, Alexander. With the silver, Peyton. And the gold, Ziriana. Yeah. Actually, modify the last thing I said. So greenhouse effect too. So from the greenhouse effect, you're able to radiate less energy than you otherwise would. All right. So I got for you guys. I know we have just a few minutes left here. Where is this? Here you go. Okay. Got a Mark Rober ready for you guys. He's going to test this self-driving car technology. Is the car going to run into a Wile E. Coyote style wall? We will find out.
The car automatically saved itself from crashing because it uses a LiDAR sensor.